Okay, good afternoon, everyone, and thank you for the introduction. My name is Yu Ono. I'm from the Carleton University in Canada. Today, I'd like to talk about our development of the flexible and wearable ultrasonic sensor for the continuous monitoring of the skeletal muscle. So this is a study of my PhD student, Ibrahim Al-Mahid. So I'm talking about on behalf of him, and I'm the supervisor of the student. Outline of my talk. First, I'd like to talk about the background and motivation and some challenging of the muscle monitoring using ultrasound and objectives. So then, sensor design and the construction for the ultrasonic thickness measurement of the skeletal muscle during the contraction. So some demonstration for the in vivo measurement using a human leg, then the summary and the future study. So the muscle monitoring, there's a various technique already available nowadays. For instance, electromyography, EMG, or mechanomyogram, MMG. So this tensiomyography is a part of the mechanomyography which measures the mechanical property of the muscle during the contraction. This shows the measurement configuration that the muscle here, and there is electrical muscle stimulator electrode attached on the surface of the skin, then which apply the stimulus on the muscle. Then the muscle twitches and change the thickness of the muscle bed. The displacement of the muscle can be measured by displacement sensor, either contact or contactless, such as laser displacement sensor. So this shows the one example of the measurement of the displacement with the time. So you can see that the muscle twitches and increase the thickness of the thickness of the muscle, then it changes the displacement at this point. So there's several muscle contractile properties such as displacement, contraction time, delay time, and contraction velocity, sustaining time. So these parameter is related to the mechanical property of the muscles. So there could be various biomedical applications. For instance, particularly in the sports medicine for the diagnose the muscle injury, also investigate effectiveness of the rehabilitation or physical training, also the physical therapy after and before the treatment. Also in the medical application, diagnosis of the neuromuscular disorder could be diagnosed, such as the Parkinson's disease. So however, there's several challenges, particularly in the muscle monitoring, because this is a dynamic monitoring during the muscle contraction. So the main challenge could be a motion artifact. So because we are measuring the displacement of the muscle, so any undesired body motion could cause a measurement error. So because of that, many cases, as you can see in this photo, the subject could be laying on the bed, keep still, and the sensor is attached here to measure the accurate measurement, which may not be desirable in some cases that if we want to measure during the physical activity for the long-term monitoring. Also, the monitoring could be limited within the laboratory or clinical environment. So, to overcome these issues, objective of this study is to develop the ultrasonic sensor, wearable and flexible sensors for the continuous monitoring of the tissue thickness changes. So the sensor is flexible and wearable, and which could be disposable because it's low cost, which is desirable for the medical application. So the medical probe here, this is a clinical medical imaging probe, which is kind of bulky, and we want to try to develop a thin film type sensor such as this. So it's not really to replace the clinical medical devices, because this is medical ultrasound imaging provide a two-dimensional image of the internal tissue, but here our sensor is only one-dimensional, but which is good enough to measure displacement of the chosen location of the interest. So the sensor is flexible, which can be bent and fit to the soft curved body surface. So we believe that this could reduce the motion artifact and also the less mass loading effect. So measurement could be done during even the physical activities or the long-term monitoring even outside of the clinic or laboratory environment. So this shows the sensor design, the construction. So the main material is here, red one, the piezoelectric polymer material. So we choose the polyvinylidene fluoride, PVDF, which is a kind of standard polymeric piezoelectric material. And we glue the two films, each of the thickness is 52 micron, using the low viscous epoxy. Electrode material is silver ink, and we do have several more layers. For instance, the aluminum foil for the electromagnetic shielding to reduce the environmental noise. Also, the outer entire sensors are covered by the protection layer made of the polyimide films. So the multi-layer structure, in this case with the two layers, has some advantage to improve the signal strength of the ultrasound. Also, we can control the frequency of the ultrasound. So the fabrication processing is nothing fancy at the moment. We made a sensor in my laboratory, just cutting the PVDF film and with the desired size, and attached with the bonding layer, and also we solder the electrode wires. So the sensor here, in this case, the center frequency is around 4 megahertz, and the bandwidth is 4.6 megahertz, which is kind of typical frequency range of the medical ultrasound. The total thickness of the sensor is 350 micron, and total weight is about 0.4 grams. So it's quite lightweight and bendable and flexible. So the measurement method. So there are several ultrasound methods, but here we use the so-called ultrasound pulse through transmission mode. In that case, we have the two ultrasonic sensors. One is for the transmitting the ultrasound, and another one is for the receiver ultrasonic sensor. So here is the tissue sample. We attach the sensor on the skin surface with the Kaplan gel. So this shows the typical example of the received ultrasonic pulse. So by measuring the time flight of the ultrasound and using known velocity of the ultrasound, we can calculate the distance of the tissue. So we could also use a single sensor. It's called a pulse echo mode. If we have the bone inside, then we could have the deflection of the echo using just one sensor as a transmitter and receiver. But in this example we just showed here, we use through transmission mode to measure the total thickness of the tissues. So this is the experimental setup. So we attach a sensor on the lower leg, healthy male subject, and we apply electrical stimulation with the frequency from 2 Hertz up to 30 Hertz. So this shows the example of the 2 Hertz stimulation result. So you can see the about here measurement 2.5 seconds. You could see the 5 pulses. So it's 2 Hertz interval. So you can see that applying the electrical stimulation, the muscle twitches and increase the total thickness of the leg tissues, and it's relaxed completely here. So by analyzing this curve, we could get the several parameters of the contractile parameters. So at this point, I cannot discuss how this value is significant to this subject, because this is only one subject, and we haven't tested another subject. However, in the several literature, it shows that here these contractile properties can be used for the treatment progression before and after the surgery. Also, the investigation of the slow and fast muscle fiber ratio. Also, the physical training effectiveness can be evaluated based on this literature. So we believe that this can be further used for the some biomedical applications. So this slide shows the results of the different stimulation frequency from 2 Hertz up to 30 Hertz. So you can see that at 2 Hertz and 4 Hertz, muscle can completely relax, so that thickness becomes the original thickness. However, above the 6 Hertz, muscle cannot relax fully because of the too short interval between the consecutive electrical stimulation. So you can see that this is called the tetanic contraction, and the higher the frequency, eventually the muscle cannot relax at all. So the feature can be clearly monitored without the motion artifact. So using the frequency dependence of these contraction properties, we can calculate so-called fusion index here. So the fusion index is the ratio between the maximum contraction and the minimum contraction. So this light figure shows the fusion index obtained from the previous experimental results. So you can see that at the 2 Hz, 4 Hz muscle can fully relax. However, above the 6 Hz, the muscle cannot relax partially. And above the 10 Hz, almost muscle cannot be relaxed fully. So this fusion index curve could provide the degree of the muscle fatigue. Also, some literature demonstrate that using the FI curve, they can evaluate the fiber type and the fiber compositions. So summary, so we have developed a double-layer wearable ultrasonic sensor for the muscle monitoring and did some preliminary demonstration of the in vivo experiments. So in the future research, currently we are planning to evaluate the accuracy of the measurement using human soft tissue mimicking phantoms. And finally, we like to, of course, try the more different subject, human subject, female and men, and investigate the fatigue and the fiber types with more human subject. Thank you for your attention.